Everyone? Okay, good. Hi, everyone. Thanks for joining us today. Maintaining, monitoring, and also optimizing the database performance, especially query performance, it's like a very crucial activity by the database developers and also the database administrators. So it's essential for you to understand what are the different type of statistics being collected in the Postgres and how to monitor it, how to measure it, how to use it. It's another factor to be considered. In this session, we are going to talk about what are the different database statistics metrics being collected and how to use it. By the way, my name is Raj Jaikrishnan. Joining me is Anita Singh, and both are database specialists from AWS, and we help to migrate and modernize customer workload to AWS. So the agenda for today is, we'd like to talk about what are the different way the statistics is being collected, why do we need to even collect the statistics to begin with, and we'll talk about what are the different type of statistics available, and how the data distribution statistics in terms of how you're going to collect it and how you're going to even understand every key metrics, and we'll dive deep into extended statistics, and a couple of different best practices, what we have come across with the customers over a period of time. We deal with a lot of customers, so we kind of put together what are the experiences we gain from multiple different customers. What is the need for collection of database statistics? Mostly it is kind of falls under performance and then operational efficiency. Performance in the sense, suppose if you are running a query, you wanted to optimize the query, and database optimizer need to collect certain statistics to come to the particular cost. And from the operational efficiency perspective, right, database is like active all the time. It means a lot of dynamic statistics were being calculated, like what are the number of tables, what is the tuple inserted, deleted, updated, whether this index is being used or not. All the statistics which we need to collect it to make sure that it provides a better operational performance, efficiency. We're going to divide that one into like two categories. One is like data distribution or optimizer stats and the monitoring stats. The optimizer stats is the one which we are going to dive deep into the later part of the section, which basically helps you to optimize your queries and help you to understand the optimizer to come with the various execution plan and arrive at optimal plan. The monitoring stats, as I mentioned, will be collecting all the different dynamic statistics, PG underscore stat. If you look at the Postgres, right, PG underscore stat star, all the different type of metrics is being calculated and used for multiple different purposes. Why do I have unused indexes in the database? Is my index is being currently used or not? Is it a lot of sequential update is happening, or is it going for the index scan? All those metrics will be able to gather from the monitoring stats. But for this session, we'll be diving deep into the data distribution or optimizer statistics. So I just want to take a minute to explain this particular diagram, and probably everybody must have come across this one time or other time. So normally, right, when you're going to run a SQL statement, and you're running a SQL statement, you're getting the result set. And I want to talk about what is happening in between. Normally, right, you connect to the Postgres, you run a SQL statement, it is going to go through multiple different phases. First, it's going to parse the query, do a syntactic checking, semantic checking. Then it's going to rewrite it. Suppose if you are going to go using the CTE or if you're going to use the view, it's going to rewrite the query. Then it comes to the planner or optimizer. And I'm not sure actually how many of you are familiar with the rule-based optimization and cost-based optimizer. The rule-based optimizer used to be there for a long time before, like in Oracle. There, right, the optimization process is very simple, straightforward. You have a set of rules. First, you go for the first rule. If the first rule is satisfied, it's going to go over the index. If not, it'll go to the second rule, third rule. But later part of it, we start adopting a cost-based optimizer. What the cost-based optimizer does, it's basically coming with multiple different execution plans for the same query. So for example, right, if you're joining a select statement with 10 different tables, there are zillions of ways in which you'll be able to formulate it. You can go for the index scan, you can go for the nested loop, you can go for the sort merge join. So what optimizer does is basically calculate multiple different execution plan and then get the cost for each and every plan and pick up the plan which has got a less cost. Now, it is needed for you to find the cost. Just for that particular purpose, we need to collect the statistics. It means what we are trying to do is we are going to take a table, find out what are the different columns in the table, what is the data distribution, does it have a null, or what is the most frequent value used. All the information we are going to calculate in the statistics so that the cost-based optimizer will be able to make a much more educated guess of, okay, this SQL statement will have this cost, this will have that next cost. That's what the cost, the statistics is playing a very crucial role in estimating the cost, or the optimizer comes with a proper planning. There are multiple ways in which you will be able to calculate the statistics. Normal, you come across analyzing a table. And there are other ways, like if you're going to enable the auto vacuum, whenever the table is going to be getting vacuumed or analyzed, statistics is going to be calculated in the behind the scene. And also like create index, create cluster, multiple different commands helps you to calculate the statistics. I want to talk about the parameter called default statistics target. And by default, that value is 100. Because normally, right, if you have a table, and as I mentioned, right, we are going to collect statistics. Okay, should I calculate statistics for all the rows in the table? I have 1 billion rows. Will it be possible for me to go for each and every row to calculate? Practically not possible. So we are going to have a parameter which is going to give me the sample size, how much you want to calculate. So that's what the parameter is. We are going to dive deep into the parameter later part of the section, but I just want to highlight there's a parameter available. Then it's going to calculate multiple different metrics, like key values, or what is the common value, and what is the fractions, everything extra. We have a slide which we'll go through that later. All of them are going to store in a view called PG statistic, and we have a view called PG stats, where we'll be able to go and see how the values of the columns and all the different type of key metrics after you analyze the table. So just to go a little bit of how the data distribution statistics works, I have a small table created, and I did analyze verbose on the particular table. Now, if you look at the PG stats view, which I mentioned before, and I'm going to be filtering only on the particular table name. As I mentioned, every column in the table will have a single row on the PG stats table. If you have a table with the 50 columns, we'll have 50 rows in the stats. Each and every column will have all these particular metrics being calculated. The first three, it's going to tell me like, okay, this is coming from the table, this is a schema, this is a column used, please.
Just a quick question. Is this a particular Postgres version that you're referring to?
This is a version 16.
16.
Yeah. So it depends on the version. There'll be a couple of columns added for calculating non-scalar data, but this is a version 16.
Thank you.
Okay. Then we have something called inherited. And normally, right, in Postgres, you can create a table with the inherited table, or you can get a partition table. Basically, that is a flag which is going to set here. Another one is a null fraction, because every column can have a null value. And suppose if you are querying the table saying that whether the column is null or not null, we need to find out the distribution of it. So this is going to give us the percentage of null in that particular column. Average width depends upon what the data type you're going to be using it. It's going to calculate the average size of the data. And the distinct. This is another important metric. Normally, right, when you have a column, that's a possibility that the column could be unique, or it could have multiple different values. This is going to give me whether what type of distribution of the column is. If the column is unique, it'll have a -1. Or it will have the absolute value of that particular distribution. If it goes more than 10%, then it'll have a fraction. Currently, you have a -0.5. It means what optimizer thinks, right? Okay, this particular column, it's going to grow, or it's going to have distant values, more distant values. So it kind of understands, okay, I'm just going to keep it at -0.5. Normally, let me go back. Normally, end distant value, right? It's good whenever you're going to run a query, where class, right? Obviously, it is going to come back and tell me that, okay, based on this is going to be the selectivity is going to be checked. But normally, when you have a data, the column values are not going to be distributed equally. If you have a 100 records table, if you have distant 10, doesn't mean that every column will be 10 each. Obviously, there is a skewed data, or it will be non-linear distribution of the data will be there. In order to handle that, we have another two metrics called most common values and most common frequencies. In this one, we are going to have the individual column and how frequently the column is appearing in that table. So now we are going one level below. Now, assuming that everything is going to be unique, now it's not equal distribution. Let me go one level deeper trying to individually put all the column values and the corresponding frequencies, how frequently it is appearing. Now, whenever you're going to query, right, it know exactly where the distribution is, trying to figure out what the selectivity. Now, sometimes what happens is that I have a billion record table and have like thousands of unique values. It's not possible for me to fit that one in the particular most common values. And also, right, remember we talked about the default statistics parameter, which is set to 100. So I can have only up to 100 values in the most common values. If it is more than 100, what I'm going to do, I'll use the histogram bounds. Instead of having individual value, I'll say, okay, this is the bucket which I'm going to create. And then it'll have an upper bound, lower bound. So based on that, it's going to identify where the data resides. The last one is going to be correlation. It's going to find out whether how the distribution of the data available in the physical or the logical way. If there's too much of variation, then you have something around 0 value. It is very much useful in case if you want to do an index scanning. Now, we talked about all the different type of statistics, right? Where it is going to be used, especially when you do a selectivity. Now, I have the same table I'm using an explain analyze, trying to figure out what is the value of ID equal to 10. And the reason I'm using analyze is I want optimizer to come up with a plan, and also I want to compare it with my actual value. The important parameter what you want to look at is the row equal to 3. So it means optimizer thinks when I'm going to be executing the SQL statement, I'm expecting 3 rows. And actually is also 3 rows. It means I'm matching it. So whenever you are trying to tune the query, right, there's a first parameter you need to look at it. Do a explain analyze and try to figure out what is the actual row and what is the expected row. If it is matching, then probably optimizer will make a better plan. How it arrives that number 3 value? Remember we talked about most common values and most common frequencies. It's going to look at the number 5, and then most frequency is 0.075 multiplied by the number of rows, it's going to get number 3. And this is how fundamentally Postgres is going to calculate the occurrence of the selectivity. But this is a very simplest form. But in case if you're having a greater than symbol or less than symbol, if you're joining 2 or different tables, then the calculation is going to be more tedious, more involved. But this is kind of give an idea of how the Postgres works in terms of calculating the estimated rows. And also I want to talk about how the default statistics import. So now I have a table which basically have a post. We have a user ID and the number of posts by individual users. And the post type is basically text, image, or whatnot. And if you look at right, I have an uneven distribution of the data. It's like 70% of the thing is basically on the text, only 1% is audio. So it means completely uneven distribution of the data. What I want to show is right how the default statistics impact the selectivity of the column. As I mentioned, 100 is the default one. So whenever you're going to analyze verbose, right, if you look at number that 30,000, which is nothing but 300 times the default statistics target. And 300 is some kind of a magic number we come across like a hard-coded value. And whenever you analyze the table, we take 30,000 as a sample size. If the table size is less than 30,000, we pretty much analyze the full table. If it's billion record, we still take only 30,000 as a sample. In this case, right, I have 2 different indexes, one on the post type and user ID. Now, if I'm going to give an analyze, right, like user ID and the post type, what is happening is, right, currently it will be able to get the rows properly, but it is using only one index. I have 2 indexes, but it's using only one index, which comes with like 0.4 millisecond. Now what I want to do is, right, now I know, okay, 100 or 30,000 rows is not sufficient because it's not able to get the histogram bucket properly for the specific column. I want to go a little bit more. Then you can set the statistic for a specific column too. It means, remember we talked about most common frequency, most common values, the bucket is only a default statistics target. For this column, we are increasing it to 1,000. So it means it'll be able to kind of get a bigger distribution so that optimizers will be able to make a better decision. Now, if you do the same explain analyze, now it go for both the indexes, index type and this one, and then time is reduced from 0.4 millisecond to 0.1 millisecond. So effectively, what are the default values may be suitable for most of the application, but sometimes you may have to tune it, completely depends upon your data set. If the data is completely skewed, then probably we have to gather more information for the optimizer to make a better plan. With that, I'm going to hand it to Anita to continue.
Increasing that default statistics, starting particularly on large tables, what are the performance implications for something like auto vacuum?
Auto vacuum also, right, it's going to take delta value. So definitely it is going to be, it'll be taking a little bit more time for the calculation. But that's the reason we tend to use it only for a specific tables, for you don't want to change the default statistics to 1,000 for a whole instance. Just for a specific table or specific column, which you know it's highly distributed, highly skewed data, then you just use it only for the day. But definitely it'll take longer time to do analyze.
Okay, thanks. Can we, sorry.
Can I take the question offline?
We are hard pressed on time, so thank you. All right, so we as humans, we understand the relationship between Honda and Civic, Toyota and Corolla, but this information is not, it's something that Postgres doesn't know. So in order for us to inform Postgres about these relations between the different values, we need to create extended statistics. And this section, we are going to be focusing mostly on extended statistics because Raj did provide a good base as to how the estimates work and how better estimates help us improve the query plans. So extended statistics are where you would create when there is correlation between different columns. Like I gave a very simple example of manufacturer and a model of a car. Similar to that, there are a very other common example is city states. So such columns, they have dependencies. And in that case, extended stats come in picture. Extended statistics are something you can create with a simple create stats command. And we'll dive in deeper into the majorly extended stats can be classified into these three different categories. One is dependencies, NDistinct, and MCV. MCV is the most common values, which I think Raj did cover to a bit extent. Now the functional dependency is something where there are two categories in that. You might have a query which is using a function in the where clause. It can be like a truncate, substring, or things like that. So for those kind of functionality, you can create extended stats as well as you can create a functional index. So by creating extended stats, it's a less load on the system. But at times, you might have to switch to creating indexes as well, but that is what functional dependency provides. So you can create a stats on that. The other thing is dependency, like what we have been talking about. If you have columns that are correlated, it can be two or more than two columns, and you define that. With NDistinct, so let's dive in deeper into each because we are a bit pressed on time. So here, a very simple example, we have created a simple table, cars, with two columns, make and model. And we inserted about 1 million rows. And as you can see on the right, the data is skewed. We have only 0.5% of the data that belongs to Honda Civic, whereas Toyota Corolla has 98% of data. So just keep in mind that we have skewed data. Now, when we run a query like this without any giving any additional information to the optimizer, what it does is it predicts that this query will return 23 rows, whereas the actual rows returned is 5,000. So there is quite some misestimates. And to improve these misestimates, what we do is we create stats. The first command that you see, that's the simple command to create statistics. We say create statistics and then put dependencies because we are asking it, we are telling the optimizer that there is dependency between the two columns, make and model, right? If you exclude the dependencies word, then by default it creates all the three types that we spoke about in the previous slide for the same column set. Now, after creating the stats, you do need to analyze because creating that extended stats, it's just putting in an entry into the stats extension table. But after you analyze, the optimizer is able to use that data, and now you see that its estimates are very accurate, right? It's estimating at 5,000, and it's getting. So once those extended stats are created, it goes in and you can go and view this PG stats extension, ext view, which tells you, it has an attribute called dependencies, which tells us how the columns are related. Like what's the dependency factor? Like if you see 2 to 1, which is like each model belongs to a particular manufacturer. Like Camry belongs to Toyota. So that's why you see the dependency as 1, because that's only, it's unique. So this kind of data is available, and this is what the optimizer uses to further plan the query. Now, end distinct is something that comes in handy when you have queries where you are doing group by on multiple columns. So aggregated queries benefit from end distinct functionality. What end distinct does is it just creates an entry again in the ext, pgstats ext, stating the relationship between the columns in terms of unique, like how many unique values are available in the data set for those columns on which we have defined. So here again, you see that we are running a simple query, explain, analyze, select, count star, and group by the 2 columns, model and make. And here, again, it's misestimating. We are seeing that it's estimating at 6, but the actual rows returned are 3. Now, after we create this extended statistics, again, analyzing, it comes to more accurate prediction. Right? So this is the impact of extended stats. And after each test, we did drop the stats, extended stats, just so that it's not influencing the other test. The third one is, now these 2 that we discussed, as we saw, that's just storing statistical data. It's not storing the actual values. So that's when it can make some kind of predictions, but if you want to go more granular, the most common values come in handy. And through this third set of extended stats, we created saying that we want MCVs to be generated for make and model. Once we create the stats, you will see that this data gets generated. It has, I think Raj went through this, basically it's telling us that the combination of Toyota Corolla, there is about 0.9799% of data belongs to that first set of common values. So what we covered earlier was that by default, the analyzer just creates single column stats. But if you want multi-column stats, then you go and create extended stats. So over here, we have created this, and again, we see the same thing, that it's able to predict much better. Earlier, it was like estimating about 5041 rows to be estimate, and the actual was 0. And the other thing is that the distinct and end distinct and the functional dependency, that works only with equality conditions. Here, if you look at the query, we are looking at the make not equal to Honda, right? So for inequalities, MCVs come in handy, because now it knows that there is no match for Civic without Honda, right? So that's how the stats gets created, and now we see the planner estimates match the result set. So best practices around the statistics. Tuning, as we all know, it's an art. We get into the weeds of it till, I mean, there's no end to tuning. You can keep on tuning, but more or less, we have to be mindful of the parameters that we are changing. Raj did go through the default stats target parameter. Ideally, we would all love that, you know, it goes and samples out the entire table, but then there's a cost to pay. So be conscious when you are changing the parameters. These parameters, and for a reason, they have given it that you can change the parameters at column level, not even at table level. So if you want to do it at a table level, maybe there is some master lookup table, which is very important. You would have to go in and run a script or go and do it for each column. And the other thing is, like we spoke about extended statistics, when you create extended statistics, be mindful that you are putting in a little more work for the planner to go in and check the extended stats. And even when the extended statistics are being gathered, there's some additional work. So it should be worth for the query. So if you have queries, most of your queries are using those 2 columns, only then go and create the extended statistics. So be mindful of your actions. That's all about here. And one thing which we have seen with many customers that folks miss is with major version upgrades, you need to regather all the statistics because the stats are emptied out after any major Postgres version. So that's the end of it. Raj, we're 5 minutes over. Anything? All right. Thanks a lot, everyone. Thank you.